evening, and this is our current topic, pressure. As you well know, we are all under pressure, atmospheric pressure. And a question. A standard situation, we have a tank, a bucket, a column filled up with some liquid. Eventually we need to calculate the pressure, but in the meantime, the first step is calculating the weight. The weight of that tall water column, 10 meter tall, square base, 20 centimeters by 20 centimeters, and filled up with water. So as usual, if you know what to do, just do it. If you need an extra information, if you have a question, you have to act and ask a question. Oh, you're back. And of course, a weight is a force. So nothing new, nothing different every time. We start from a picture which helps us to see what's going on. Square base, tall, rectangular. It might be standing on a floor. So, of course, it pushes on the floor. That's what we call weight. A floor pushes back. That's what we call normal force. They equal to each other. And what's the equation for weight? Well, you say mg, right? And what the equation which relates mass, volume, and density? And now we get the equation you used. If we put these together, combine together, substitute m with the we get and all right, we're getting answers. Good. So at this point, we just have to start plugging numbers into this equation. And okay. If we use international system of units, that's density. G is about 10. How do we calculate the volume? Well, in this situation, the base is square, so not circular. So it's length times width times height length. And we have to be consistent in units. 0.2 times 10 is 2, 0.2 times 10 is 2, 2 times 2 is 4, 4 times 1,000, 4,000. And now we can calculate the pressure. The ultimate goal was calculating the pressure. How much pressure does it exert? So that's the weight. And the pressure, by definition, it's the force applied to 1 square meter of a surface. So in this situation, to calculate the force, we use this equation, and the pressure is force over area. And now I want to write this again. If we divide the volume over area, what's left? We use numbers to calculate the volume, but we can do some algebra sometimes, right? How can we relate height, area, and volume? So volume divided by area equals height. This is a standard expression we can use for calculating pressure of any fluid. It doesn't have to be water. And in this situation, we can calculate it's 1,000 times 10 times 10. This amounts to 10 to the fifth unit of a pressure in a Newton over a meter squared, but it also has a name because French physicist Pascal was studying, so we call it Pascal's. And actually 10 to the fifth, we will see, is also close to the average atmospheric pressure at the sea level. This pressure is purely due to water. That's what we call the gauge pressure. But if we would place a manometer, a pressure meter, a device which measures pressure here, we would have to also account for the additional pressure due to atmosphere above it. And so that's what we call the total pressure. So this is the equation which we just derived, tells how much pressure does any specific amount of fluid exerts without additional pressure which might be applied to its surface, if there is something above it. So this equation assumes nothing is above it, vacuum. However, it could have been a different fluid, air, oil. In that case, we should add to this pressure, to the gauge pressure, the pressure at this surface. And if it's just atmosphere, atmospheric pressure. And that will give us total pressure, the actual pressure. Now, this has been used many, many years ago to actually measure atmospheric pressure first time. And 1 atmosphere is about 10 to the fifth Pascal. So this is a number for the atmospheric pressure which we need to use in calculations. Because when we calculate something, we use newtons, meters per second, etc., etc. But practical pressure sometimes is measured in pounds per inch squared, torricellis, or millimeter of hydrogen column. And the atmospheric pressure, 10 to the fifth, 100,000 pascals means if you cut 1 square meter and 1 square meter is not actually very large surface. It's 1 meter and 1 meter. So the human body has very similar surface, and air pushes pressure times area is force. So 100,000 pascals times 1 meter squared gives 100,000 newtons. It's a huge force, strong force. So the question is, why doesn't it break everything? So the question is, why doesn't it break everything, including us? So I don't know. So while collecting your answers to this question, I'm going to demonstrate how strong the pressure is. These are classical experiments. One of these experiments, again, has been done in 1656 in Germany. And all you need is a pump. All those experiments became available only when people succeeded in making vacuum or almost vacuum. So we need to connect. And now just turn it. Well, first of all, you know what? This is what's happening right now. And if we try to suck some air out of it, and human lungs actually, well, it's probably a couple of liters maybe, but the force is weak enough. But now we can make a hypothesis. What's going to happen if we suck out almost all air from it? Well, that's where we need the pump. Should be sufficient. Go ahead. Try it, pass it around. Eventually someone. And today we have our own Magdeburg semispheres. You know where you get it? Home Depot, Lowe's, Ace. People use it to transport, let's say, large piece of glass. Go ahead, try it. Different sizes, very cheap. Now, a similar experiment nothing, because my lungs not strong enough, just not strong enough. So that's what the atmospheric pressure does. Why it doesn't happen to us? Still waiting for the answer, right? And by the way, the answer number 3 makes sense. Makes sense. I'm not going to go into this, but it makes sense. Well, and my favorite experiment, which works 2 times out of 3 because of many different issues. Friction might be involved, something else. This is what we call the air cannon. I'm not sure what kind of a cannon been used there. Here what we use is just a piece of plastic tube attached to the pump. We know what the pump does, you know. But all I need is just seal the ends. And in that case, we can, again, have a deep vacuum inside it. And if we let suddenly air pressure get into it, we saw it very strong. It should push the ball, and now it's there. And that force we should expect will be very strong. And you can, if you have a pump, you can do the same experiment at home. Scare your neighbors. Even if it doesn't make a shot, sometimes a tiny piece of tape gets attached to the ball gets stuck inside, but it's going to be very loud anyway, so neighbors will be scared. So we gotta see, attach. Again, where do we get this? Or Lowe's, or Ace, or Staples. See? Free advertisement. No one pays me any money for that. Okay, the ball is here. So it's very important to have a good seal. Sometimes it breaks because the pressure, atmospheric pressure, becomes stronger than it can sustain. Okay. Now we're going to catch the ball, because otherwise it will actually, not sure if you see from, but if you look at this, you see? That happens when the ball wasn't caught properly. So to cut the ball, I just want to have a catcher. We know haters gonna hate, catcher's gonna catch. So now I'm gonna need this, and while I say ready, you should cover your ears, and I'm gonna run this pump for 2 minutes to get a good vacuum inside. Not now, 2 minutes. But you can touch the seal, it gets sucked in. This is to pinch. You can hear it work harder and harder. One more minute. I can feel the pressure rising. I really hope it's gonna work today. It worked yesterday, so 2 out of 3, good chance it will. Ready? Close your ears. It did work. So, let's go back to our question. You can keep it if you want to. Or pass it around. If the atmospheric pressure can exert so strong force, why doesn't it affect us? What do you think? What did you answer? Well, in that case, you have to offer your own explanation. All right, well, someone should offer an explanation. It doesn't have to be correct, it's hypotheticals, but if you choose none of the above, you should say something instead.
Does it have to do with the fact that we have a certain pressure that pushes outwards? That's the thing.
And why would we have that pressure which pushes outwards? What's the reason for that? What do you think?
Pressure is always on us.
Right, but did you see the can? Yes?
We also have air that's inside of us.
How did it get inside of us? Hmm? That is what?
I guess we have our own density. So
You're changing your answer. You said air is inside us, and then you say it's because we're dense. Well, yeah, maybe. Like this? Like wood? No, not. I don't remember the exact number, like 80% of us is water, not wood. So, how did air get inside us? For example, through breathing. Where else? Where else? Hmm? Well, how did it get into the blood? Through what? Through what? What about ears? What about eyes? What about skin pores? We have holes everywhere. The can didn't. That's why it crumbled. But the same air, which pressures from outside, gets inside and pressures outside. It cancels it out. And if that wouldn't be happening, let's say you are in the outer space, and that internal pressure is not being compensated by the atmospheric pressure anymore. What's going to happen? You explode. That's why people need the spacesuit, not because of the oxygen deprivation. If it would be just for oxygen, they could use just a mask with a tank, but that internal pressure would blow them up. That's Arnold Schwarzenegger. Well, okay. Let's solve it very quickly. We know what to do. It's basically the same problem we have solved before, and now we can do it differently. We can calculate mass and then calculate volume, or we can just use something else, like pressure. Doesn't really matter. This is what we're looking for, right? And the only difference here is the .1 of a meter. The beaker is circular, so the radius is 0.1 of a meter. And why do we need the radius? To get the area. So this is what I want to do. I want to use this equation. Height will be equal to pressure over density times g, and the pressure should be equal to force over area. That's it. So force, that's what we read here, 30 newtons. Now, actually interesting also fact, when we place something on a scale and we read a number, we assume that number tells us the weight, but now we know that technically there is atmospheric pressure which also pushes on a surface. That's huge. We don't read it. Why? Because of the same reason. The same atmospheric pressure also pushes from below the scale. That's why the reading represents pure weight. So 30 newtons divided by area. Area should be equal to pi r squared. And that should be equal to the density, which is 1,000. And that should be equal, divided by gravity, which is 10. So 30 over pi, 10 to the fourth, 10 to the negative second. Well, I can make a rough estimation because pi is close to 3 over 3. So what do we get? We get 0.1, about, close, of a meter, about 10 centimeters, but probably 9 centimeters something. You can calculate it. Something like that. Well, and another interesting fact, remember this experiment, when we keep inserting ball in water, the reading goes up because of additional force. But now we know, of course, if we just would be pouring more water, the reading also would go up. And turns out, we can prove it very easily if we want to, when this height is equal to that height, the reading will be the same. The pressure depends only on the height, same area, same force. And this is, again, just a note. We used that equation as a fact from experiments, but technically, we can actually mathematically derive it if we want to. If we have an object in fluid, the pressure changes. Yeah, the pressure from right to left and left to right cancel each other out at the same levels. But here we have lower pressure, higher pressure, so there's net force. That net force is the buoyant force. We can calculate it. Now we're moving on to situation when something flows. Everything we said so far was related to static fluid, no motion. Now, fluid dynamics. These are our assumptions. An ideal fluid, so no friction, incompressible, no rotational, etc., etc. Basically, an ideal fluid can be treated as a large set of ideal tiny particles traveling in space without friction. So we can basically apply all mechanics we've learned before for a single tiny fluid particle, and that's it. For example, first conclusion comes from the fact we cannot compress it. If we cannot compress it, that means the amount of fluid which travels through the pipe every second is the same. If 1 kilogram enters the pipe here, in a second, 1 kilogram have to leave the pipe in a second. Of course, it would have been different if we drilled the hole, for example, some fluid could lost, or we could add some fluid, or we could compress it. But if it's incompressible, that's it. The amount which travels through every cross section of a pipe every second has to be the same. This is kind of law of conservation, but we don't call it conservation. We call it a continuity equation. First, this ratio, number of kilograms traveling per second, has a name, mass flow rate. And you can see for any fluid it equals this product, density times area times velocity. But because the fluid is incompressible, density is the same everywhere, we can write this expression. Mass flow rate at first point should be equal to the mass flow rate at any second point. And since density is the same, it's getting canceled. This is the equation we call a continuity equation. And this product tells us how much cubic meters per second travels in pipe. That's why we call it a volume flow rate. Volume flow rate. How many liters per second? How many meters cubed per second? And again, this looks like a law of conservation. So sometimes people used to call it law of conservation of flow amount. The amount of volume remains constant, remains the same. That's the first equation. And you can see in this picture, it doesn't really matter how pipe is shaped. It's not about pipe, it's about fluid. If it's incompressible, ideal fluid, the continuity equation always works. Second, what we know about motion. A moving object has kinetic energy. If kinetic energy changes, net work is done. That's what we know. So if we apply work kinetic energy theorem, or, because no friction, law of conservation of mechanical energy directly to a fluid, we get an equation which has a name, Bernoulli's equation on the next slide. I just want to say that since fluid, well, it's not actually a particle. To describe its motion, we use 1 cubic meter of it. So we look at the motion of 1 cubic meter as a fluid particle. The mass of 1 cubic is density. Force acting on 1 square meter is pressure. So if we apply work kinetic energy theorem or law of conservation of mechanical energy, the equation, which has a name Bernoulli's equation, again, physicist, Italian, looks like this. Again, it's just a straightforward law of conservation of mechanical energy written for 1 cubic meter of liquid. That's gravitational potential energy. That's kinetic energy. That's force acting on 1 meter squared. And this sum remains the same. So now we have two equations we can apply to describe an ideal fluid traveling through pipes. So if you have to solve a problem when fluid flows, you have to write two equations. And writing equations doesn't require thinking. It requires moving your hand accordingly. Only then you can start thinking, okay, how can I rearrange maybe something algebraically, what I know, what I don't know. But until then, just straightforwardly write equations. Now, how does motion affect other parameters like pressure, speed? Well, let's see. This is, again, a classical experiment, one of the version of venturi tubes, which people used to use to measure speed of flow, speed of air. And all you need is a source of fluid which can travel fast. This is the pipe. These are devices to measure pressure difference. So right now, here and here, the pressure is the same. Here and here, the pressure is the same. And if I see something different, let's say I see that this level goes down, this goes up. What does it mean? Where pressure is higher? Here. If I see something like this, that means pressure will be higher. So this is a pressure manometer. And air will be traveling through the pipe. Same. More pressure. The most important part in this demonstration, do it slowly. Some faculty forget and open it, and it shoots out. And everything is green. So how can we explain this? Well, now we know how. We have two equations. First equation, the continuity equation, tells nothing about pressure, but it tells something about speed. So this is important. In this part of the tube, you see, this tube manometer is connected to the pipe with the same diameter. Same diameter, same area, same speed. So now we can go to this equation. Same height, so no potential difference, no difference in potential energy. Same speed, same kinetic energy, which means the pressure here and here are the same. That's why we don't see any difference here. But a next part of the tube is different. See, it's connected differently. Here it's connected to a wide part of a pipe, and here it's connected to a narrow. So first of all, if you have a garden hose, attach it to faucet, turn it on, and you squeeze the nozzle, it shoots higher, higher or longer, because it starts traveling faster. Why? Because of this equation. If area becomes smaller, to compensate that, speed should become higher. So when pipe getting narrower and narrower, the speed of the flow is higher and higher. Liquid starts traveling faster and faster. So air traveling here has speed higher than air traveling there. Well, first of all, what is a pressure? The pressure is a result of millions of molecules hitting on a surface, like a ball. When it bounces back, it exerts force. When millions of molecules bounce back, they exert stronger force. So since here we have slower motion, those molecules, air molecules, have more time to hit on the surface. That's why the pressure is actually higher, but we also can use this equation. Again, first of all, in this experiment, height doesn't matter. Same height. We set it to 0. Now, we know that at point, let's say B, at point B, air flows faster, which means kinetic energy is larger. But the sum must be the same, so if this term goes up, this term should go down to compensate that. And of course, if we had numbers, we could have calculate speed, we could have calculate pressure. Any questions? We will be solving specific problems. Well, a couple of more demonstrations. When the ball is right above the funnel, it doesn't surprise us. Yeah, we can expect there's a force which keeps it, but when it's actually away at a certain angle, that's something interesting. And I do have where is it? A golf ball. You know that the golf ball is heavy. And I can try the same experiment with the golf ball. Of course, gravity makes it fall, but now it's being kept. At a certain point, the force due to pressure difference is not strong enough to prevent it from falling. So all these experiments have the same explanation. When air flows around something, if it flows at different speed, there has to be also pressure difference generated. And well, in the first experiment, yeah, faster flow means lower pressure, slower flow means higher pressure, high pressure, stronger force. So we have a net force acting up. How do we use it? Very heavily. That's why they fly. A wing is made in such a way so there's a net force which lifts that whole thing up. Well, I've got a couple of more which I like because they're loud, which is good in the morning. Where do you get this? Or Lowe's or Ace? I'm going to ask you to help me to hold this. This is much heavier than this. Well, that's why we need much stronger flow, right? Now, oops, let's try this one. This should be related to one of the lab questions. What happens? Exactly the same thing. The flow grabs it, and this is very expensive. I need to keep it. You could have done just this. What's happening? Well, exactly the same thing. There's airflow above and no below. So fast, slow. Fast means low pressure, slow means high pressure. That's it, lifting force. Well, now, theoretically, you can solve problems related to all this material. But before that, I need to talk about gravity, and only then go back to specific problems. What do we know about gravity? Well, thanks Sir Isaac Newton, everything. This is his fourth law. Yeah, we know first, second, third, the universal law of gravity, people call fourth law, and it's very well known. I'm sure everybody have seen this equation at least once, maybe more times. It tells that the magnitude of the force of gravitational attraction between two objects is proportional to the product of their masses and inversely proportional to the distance squared. Distance between what and what? If it's a small object and another small object, just between the objects. If it's a small object and a big object, between the center. That's people sometimes forget, not from the surface, from the center of the big object to the small object. And if you have two big objects, from the center to another center, that's it. And that's the magnitude, and there is no gravitational repulsion, doesn't exist. So all objects attract each other. We all attract each other right now. But that force is so tiny because this coefficient, the universal gravitational constant, is tiny. So if you use 1 kilogram, or like 100 kilograms, and 1 meter, the force will be 10 to the negative 9, nano. It's immeasurable, we cannot measure it. So to generate a strong force, we need at least one large object. That's what we call a planet, for example, or a star. So only between large objects, gravitational attraction is strong. And now we also know that gravity does work, sometimes positive, sometimes negative. The equation we used to use, mgh, for potential energy, works only when we are close to the surface. That wasn't the exact expression for calculating gravitational potential energy. This is the exact expression, which works for any situation. Same constant, product of two masses, but the difference between energy and force, first, a minus here, and second, no square, just distance. Now, we're going to talk about a couple of different situations. First situation, when you have two objects or three objects interacting, nothing is moving. In that case, you have to draw a free body diagram, calculate force, and that's it. We've done it before. And another situation when we have an object orbiting another object, like a satellite or orbiting Earth or a planet orbiting star. First of all, of course, we're going to talk about the easiest case, circular trajectory. And what do we know about circular motion? Everything. So this is not a new situation to us. It is a straightforward application of everything we have learned about circular motion combined with Newton's law of gravity and Newton's second law. And now, theoretically, you can solve all those problems. No new knowledge. We just need to practice. And let's practice. Here, a very standard situation could have been a siphon, a fountain. You have a large tank or a bucket, a hose attached to it. You want to make water shooting up. And in this situation, we need to calculate how fast it will be leaving the hose. Is it about gravity? No. Is it static fluid? No. It's a moving fluid, which means we have to use two equations, no thinking. First equation, a continuity equation. Second equation, the Bernoulli's equation. Now we can start thinking a little, not too much, not too hard. First of all, in this situation, you don't know it, but I'm going to tell you right now, we have to make certain approximations. For example, if you look at this picture, this area is much larger than area of this hose. How do we write it? A2 is much greater than A1. It matters, it's important, because this tells us something about speed at the top, V2. V2 should be equal to A1 over A2 times V1. So this speed, V1, natural speed, well, maybe meters per second, whatever, but still, this ratio, A1 over A2, we can actually make an estimation. For the hose, let's say diameter is about 1 centimeter. Pi times 1 centimeter over 2 squared. And for a tank, let's say large tank, diameter 10 meters. 10 meters, if I use centimeters, it's 2 zeros. So pi 10, 0 centimeters over 2 squared. Pi is getting cancelled, 2 and 2 getting cancelled, so this ratio is about 1 over 1,000 squared, which is 1/1,000,000. So this is practically zero. Which means we can neglect the motion of the surface in the tank. It is practically zero, it's negligible. So V2, no matter how fast water travels when leaving the hose, this is practically zero. And we know the more zeros, the better. Now we have to use the Bernoulli's equations, and to do that we need to choose the origin. And these are the points we use to consider the motion of this fluid. So the natural choice for the origin is at the lowest of these 2 points. So this makes this to be equal to 0. This makes this to be equal to what? 0.3, yeah, not 30 centimeters, 0.3 over a meter. Now we can use the equation. So again, and we should say something about the pressure. The surface number 2 is open to the atmosphere. The surface number 1 is also open to the atmosphere. So what does it tell us about the pressure? If a surface is open to the atmosphere, the pressure is supposed to be just atmospheric. If I close with the finger the hose, that's it, that makes the pressure different, but it makes fluid static. If I place a lead on the top of it, that makes a difference. It actually prevents fluid from moving very quickly because there will be no pressure above surface 2, and atmospheric pressure there will be much stronger. So, but when we open or we make a hole, so right here the pressure, of course, is, well, for this column it's practically static pressure because it's practically not moving. But if I make a hole, that's it. The pressure immediately balanced to atmospheric pressure. And this makes our equation very, very simple. Well, first of all, we can cross them out because they equal. And what we have is this equals this. Turns out, even the type of liquid in this situation doesn't matter. We can calculate the speed using this equation. And this is actually not a new equation to us. If I release the ball and it travels 30 centimeters, that will be the speed of that ball. Which is kind of natural if we say that the liquid is ideal. No friction, nothing, no internal friction. So it's basically like a roller coaster. It travels exactly like a ball on a roller coaster. From the top, then to this point, no difference at all. And now we can calculate the number, what's going to be. 2 times 10 times 0.3 square root of 6, right? Meters per second. Any questions? Yes?
What would that 27 years
Nothing? No? I have it here because I want to ask you this question. What do you think? We just have found the speed here is square root of 6. 2 point something, 2 point. Again, it is an ideal fluid. So no friction, nothing. And you can look at the picture. It's the same hose until it's getting attached here. And what do you think should be the speed here be equal to, if we compare it to the speed there? And while you're answering this question, now we can talk about, well, why 20 centimeters could matter. Well, that could matter if we would need to calculate pressure at point B. In that case, every question related to a pressure has to be answered using Bernoulli's equation, because continuity equation doesn't involve pressure. But for Bernoulli's equation, we should choose point 1, point 2. Now we keep the same point 1, and this is not point 2, that's point B. So we should write pressure at B plus should be equal to pressure at 1, which is atmospheric, plus and now you have two choices. You can keep 0 here. In that case, that would be some negative value. Or you can change 0 to the bottom. It's up to you. And solve this equation for this variable. But in order to solve this equation for this variable, you have to say something about that speed here. How fast does it travel? So how fast does it travel? What did you say? Yeah. Same? That is correct. Yeah. So if you're not sure, but that means your intuition is correct. So it's not about thinking, it's about using equations. Same area, same diameter, same speed, nothing else. Oops. Come back. When we talk about speed, this is the equation we need to use. And if you look at the picture, well, the hose doesn't change its diameter. Same. So same diameter, same area. Where did it go? Where did it go? Everything I wrote. All right. At least this stayed. Okay. All right. I'll put it back. But same area automatically means same speed. That's it. Okay. Water travels through rectangular pipe. Rectangular pipe looks like this. It's like a air duct. So that is the speed. 10 centimeters. Oh, okay, 10 centimeters by 10 centimeters. And this equals 2 meters per second. Mass flow rate. Well, for the mass flow rate, we have two possible equations. One is a definition. It tells how many kilograms travel per second. Normally, we don't use this for calculating the mass flow rate. Normally, we use this for calculating how much fluid travels in a minute or in an hour when we already know mass flow rate. And to the mass flow rate, we already had an equation like this. This is actually volume flow rate, this product. So we can calculate both. The difference is just what we measure, volume per second or mass per second. So let's do volume flow rate. Yeah. That should be equal to V times A, and people very often confuse V's. You know, there are many, many V's. V represents speed, V represents velocity, V represents volume, volume flow rate, Valentin Voroshilov. So you have to keep track of a meaning of that V you use. That's speed. So 2 times area, 0.1 times 0.1. So 0.02. That should be meters cubed per second. Mass flow rate, just multiply this number by the density. 20 kilograms per second. It's straightforward. Now, how many kilograms travel in a minute? Well, delta M equals mass flow rate times time. So 20 times 60 seconds. Now, a hose. And two situations. We attach a nozzle or we attach a shower head. Both important, right? So, at first, well, first of all, hose has a circular area. That's important for calculating area. And the speed inside is equal to 5 meters per second. We attach a nozzle, so it's getting narrower. This is A1, this is A2. And that speed should be higher, of course. Actually, we know it. 10 meters per second. Okay. And what are we looking for? The diameter, d2. Because d1 is given 2 centimeters. Since it's related to speed, the equation is a continuity equation. Pi diameter over 2 squared times 5 is equal to pi diameter over 2 squared times 10. I like writing this way because I can cross pi's, I can cross 2's, and what I see actually is that d1 over d2 squared will be equal to, well, v2 over v1, or 10 over 5, or 2. So now we're going to take a square root of that and solve it for second diameter. It's actually 2 centimeters divided by square root of 2, 2 over square root of 2, square root of 2. So about 1.4 centimeter. Usually questions related to velocity and diameter are really simple. Now, I'm not going to solve the whole part B, but what is happening now? Instead of a nozzle, we have a shower head. Still A1, V1, V2. The question is, what should we use for A2? Well, of course, we should use only area which is open, available to fluid, not the area of shower head, but the total area of holes. So we know the number of holes, n, 30, and well, each hole has a certain area, so it's n times pi times diameter over 2 squared for the holes. And we can write the same equation again. A1 V1 should be equal to n times pi diameter of a single hole over 2 squared times V2, and solve it for the speed wherever it is. It's a very straightforward calculation usually. So you just need to keep in mind the area open, available to fluid should be a part of the consideration. A big horizontal pipe has a certain diameter, and then it bends and goes 20 meters up, widens up, and we know pressure here, we know pressure there. We need to calculate basically speed. If we know speed, we can calculate volume flow rate, we can calculate mass flow rate. So, the ground level, a pipe goes up, gets wider, doesn't stop here, of course it goes, there's something else, tank somewhere, it doesn't matter. This is A1, it travels at certain speed, there is certain pressure here, which is given to us at the ground. Pressure is 2 atmosphere, and I've seen people using 2. You cannot use a 2 because the unit is wrong. We have to use international system of units. We have to use pascals, 2 to the 5th pascals. That's the second area, A2. It travels here slower. We know it, it has to slower. And a pressure here inside the pipe P2 equals 6 kilopascals, 6 times 10 to the third pascals. All right. Very straightforward. Not thinking, writing two equations immediately. A1 V1 equals A2 V2. P1 I used to write, right? Let's keep it consistent. Now let's start thinking a little bit. First of all, we need to choose the zero level, and of course, natural choice it is at the ground, which makes this equals 0, and which makes this equals 20. So now let's use numbers. So the continuity equation says pi 40 centimeters divided by 2 squared times first speed should be equal to pi 80 centimeters over 2 squared times V2. Any questions? Why I like this expression? Because again, I can cancel a lot of things immediately. For example, I can solve it for V1. It should be equal to pi and pi cancels, 2 and 2 cancels, and this is what I can combine: 80 centimeters over 40 centimeters squared times V2. And we can see centimeters and centimeters canceled as well. 80 over 40 is 2. 2 squared is 4. That gives immediately the relationship between the speeds. Unfortunately, it doesn't give the speeds. But we have a second equation, which means have to use it. So let's use it. 2 times 10 to the 5th plus 0 plus density of water times unknown speed squared divided by 2 should be equal to 6 times 10 to the third plus density times gravity times height plus, okay, I'll fit it here, density times V2 squared over 2. All right. That arrow tells me I should have an extra slide. Yes, I do. So, the equation, let's just simplify. What do we have on the left-hand side of the equation? What do we have on the right-hand side of the equation? 6,000. 2 with 5 zeros and 5. Well, equation tells us wherever it tells us. Again, we can cancel this. And what's left? 500 times V1 squared minus V2 squared equals 6,000. But we know from the continuity equation that V1 is equal to 4 times V2. So our equation can be simplified: 500 times 4 times V2 squared minus V2 squared equals 6,000. No, you can't do that. It's wrong. What's wrong with that? I made a mistake, huge mistake. Everybody makes mistakes. Mistakes are inevitable and unavoidable. It's no shame to make a mistake. The shame is to stick to it. So, yes? So what do I have to do to fix it? I have to square the whole thing. In mathematics, words whole thing represent parentheses. Two things. So first, 4 squared 16, 16 minus 115, V2 is equal to 6,000 divided by 500 divided by 15 square root of that. And second, please do your thing. You know what to do. And we are done for this week. Good morning.
That's a good question. Okay, yeah, that's a good answer.
Don't know what went wrong on this page. I looked over the test yesterday, and it took off half a point.
Wait like maybe 3, 4, 5 minutes.
You got it.